Respected sir, I am Parth Tyagi, and I'll be giving the project presentation of our DSL group project, Facebook Print Recommendation, using graph algorithms. And other team members in our group are Rahul Sharma and Prasun Kumar. So, starting with the objective of our problem statement. So, basically, the objective of our project is to predict the existence of link between nodes using the snapshot of social networking data. Now, why is this equivalent to predicting the existence of a link? Because we want to predict whether two individuals are can be friends or not. Individuals are stored as nodes. So basically, this problem is equivalent to predicting whether or not the two nodes can have a link, and that is why it is a classification problem. So basically, just giving a quick overview, as I already told in the previous slide, that given a snapshot of the social network, we try to infer which new links can be found among its members in the near future. So basically, as I mentioned earlier, it is a classification problem, and we try to predict whether a link or not exists or not between the two nodes. So just quickly telling the concept that we use. Traditionally, the graph datasets are stored in form of adjacency matrix. Now, if we analyze adjacency matrix, for example, if we have 10 billion users, so what happens is that adjacency matrix will have 10 billion cross 10 billion size of a matrix. Now, that will be a huge size matrix and will require significant storage. Now, to stop that fact, most of the entries will be zeros and it will be a sparse matrix. So it is an inefficient way of storing data. So what do? We store the data using adjacency lists, which is based on the concept of linked lists, as we've shown in the photo here, that if two nodes are connected or not for each particular node, for example, we have four nodes, 0, 1, 2, 3, 4. So we have 0, 1, 2, 3, 4, and each of them has a linked list that which all neighbors is the node connected to. And this is way more efficient than storing data in form of adjacency matrix. And this has been used in our project as well. So basically, giving a data overview, what is the kind of data that we had? We had around 94 lakh rows and two columns. One is a source node and another is a destination node, that is which two nodes are connected. Then we had around 8 of these 94 lakh rows. There were around 18 lakh 62,000 unique individuals, which were the users. So this is a broad description, and then accordingly we had 94 lakh edges also around that number. So this is the data description. Now, we also made use of in degree and out degree as a feature. So we want to explain that concept as well. So basically, in degree is the number of incoming edges to a node, and out degree is the number of outgoing edges from a particular node. Now, in this data set, we got the average value of the in degree and out degree to be the same, which was equal to 5.0679. So this was one of the features that we used. Then, now we just, as a part of exploratory data analysis, we just wanted to show as well that how the top 200 rows of the data set we select and then plotted in form of a graph structure. Then how does it look? This is how it looks, that how nodes are connected to each other. And this is just the top 200 rows. Now this only, and still it looks really dense. So despite just 200 rows, and that is why we sort very few number of rows so that it is visible and we can make inferences out of it that yes, it is actually a we can get a feel of it that it is a graph based data structure. So now continuing with the exploratory data analysis, we just did two aspects of it to give an intuition of the approach. So basically, one is the number of followers for each of the person. Now we see that this is a very skewed graph, that most of the people have very few followers. It can be seen very clearly from this. Another thing is that the converse from this, that number of people each person is following. Now, again, this has turned out to be an extremely skewed variable. Now, coming on to data pre-processing, now we need to prepare a label. We are not given with a target variable and we need to create asset. Now, how do we create it? So basically, we create it by assigning 1 and -1 to each of the rows. Now, how do we assign it? If two nodes are connected, then we assign 1 to it. If they are not connected, we assign -1. Now, how do we split the data? Now, training and test bed was done separately for connected as well as disconnected nodes. So it is kind of splitting on the basis of by variable, which makes some sense also, because we don't want skewed distribution in either of the training or test set. As a result, we got training around 75 lakh rows and test data around 18 lakh rows. Now, coming on to feature engineering, how did we do the feature engineering part? So first metric that we leveraged was based on neighborhood. So basically, if we see that take neighborhood of VI, we take two nodes, VI and VJ. Then we analyze the number of common neighbors to both of them. This was used as one of the features. Then another is using calculated using Jaccard coefficient, which is the formula is shown here, and which is the number of common neighbors divided by total number of neighbors. This way we calculate Jaccard coefficient also. So next feature was cosine-based distance. So here we leveraged the concept of number of successors to a particular node, and based on that we computed the cosine distance, the formula for which is mentioned here. Then another feature that we computed was Cantor similarity, which is based on Cantor centrality. Now what is done is that it computes the centrality for a node based on the centrality of its neighborhood. So beta, what we see here is inversely proportional to the length length between the two nodes. So this is the generalization of the eigenvector centrality that we all know. So going to the next feature, how did we do is that we use Adamic or also known as ADAR index. So basically the intuition and the formula of it is here. So the basic intuition behind it is that we analyze between two given nodes, what are the common neighbors, then we go to each of the neighbor and then see how many neighbors it has. If it has very few neighbors and then it is connected to VI and VJ, that means that it is very likely that these two should also know each other. So therefore, it is inversely proportional to the number of neighbors of the neighbor. This is the intuition behind it, and this was used to compute the features in our data set. Another feature that was used is the other person falling back on, that is a binary variable, and which is pretty self-explanatory. So we added the following features to the data set: Jaccard distance, cosine similarity, number of followers, ADAR index, is the other person falling back or not, and then we computed shortest path between source and destination. And we have not included it here due to paucity of time, but we used Strass algorithm and Sprint algorithm to compute the shortest path as well, which has been added and explicitly explained in our report. We also use CAT-SCORE and PageRank to compute the features for the dataset. Now, coming on to the modeling part. Now, we have a final data set if we talk about the number of features that have been added by us by using all of those similarity metrics is 56. We have added 56 variables using all of these concepts that we have just described, and the formulas and code snippets of which were also shown. And the target variable, as we initially described, is a binary variable, whether or not a link exists or not. So basically, once we have prepared it, we are using the graph mining algorithms. We've created the features, we've created the target variables. Now we explore two machine learning algorithms. One of them is random forest, another is XGBoost. Because from this step onward, it is purely a classification problem. So we want to optimize both of these algorithms. Starting with random forest, we see that we plot F1 score with different number of estimators, that is the number of trees. And as shown in the table below, we can see that at the value of 250 estimators, we get the highest F1 score. And we ran multiple iterations, and these are the number of trees for which we ran it, and this was the corresponding F1 score graph. And graphically also we can see, and from table also we can see that at n estimators of 250, we get the best performance. Okay, so now moving on to the next part of optimization process, that is based on max step. So we, as you can see on the table as well as in the graph, At around 20 max step, we have a sort of saturation in performance, and after that, it's pretty much constant. So therefore, we took the max step as 20 because after that, results are not increasing, and it will only add to computation complexity without giving us any lift in the model performance. So now we tune it. Now we will tune the four different parameters together using random search CV, and the four parameters are number of estimators, max step, minimum sample spread, and minimum sample lead. Now, based on this, the best parameters that we got, we have plotted the confusion method as well as the ROC curve for that, and we get a reasonably good ROC value of 0.93 as we have shown here. Now, coming to the next algorithm, we pretty much follow the same steps of procedure of optimization. We do a random search and find the best parameters out of that the random search. So here we have shown the F1 score of the best performing model, and on the training set we got 0.9924 as the F1 score, and on the test set we got 0.92 as the test score, as the F1 score. So this is the ROC curve, and this is the confusion matrix for the best model, and we see that the ROC curve is 0.93, which is again good. And we also saw the feature importance of the XGBoost model as well as the random forest model. Now, for one thing that we want to convey here is that we see the weights that we created using the multiple metrics, that the shortest path or ADAR index. All of them are classified as weight underscore F1, F2, F3. We do see that these are pretty important variables, and also when we calculated the shortest path using Dijitra's algorithm, that is also coming out to be a pretty significant variable. So basically, the variables that we created are actually having strong predictive power when we look at the target variable. So coming on to the analysis of feature importance of the random forest, we see the PageRank algorithm that we use is coming out to the most important variable. Again, the Digitra algorithm that we used is giving us good results, as the predictive power of it is also very high. Now, we give the final conclusion. We see that F1 score of XGBoost on both the training set as well as the test set is better. And that also aligns with our prior understanding that boosting methods slightly outperform the bagging methods. And here also we got to see the same, that XGBoost is giving us better performance and very good performance, because the F1 score of 0.9262 on a test data set is a good score. And that is why we can say with reasonable confidence that our prediction algorithm of Facebook friends has been a good one. And as we discussed in the previous two slides, that measures such as PageRank or Digitra algorithm based shortest path computations, or hubs or SVD or CAD are coming out to be very important features. One thing that we note is that a follow back feature in the random forest was not having very high importance, and the reason is that if both of them know each other, then there is a high chance that they will be already connected. So that is why in that random forest was not coming, and XGBoost, there was high correlation between follow back and some of the weights variables, and that which were having high feature importance, and that is why it did not come here. And so basically the correlation is the reason why it came in one and did not come in another. So this is our final conclusion, that XGBoost is a better model and with having reasonably good performance. So this has been our project. Thank you so much, sir.